You got a meeting in Copenhagen?
Some of them did, yes. Hello? Testing. Zoom. Okay.
Does it work?
I hope so.
Are we supposed to hear anything, or is it purely for online purposes? Yes? Good. Okay. Good afternoon. Welcome, everybody. So a second in a series of talks about gamma ray burst and gravitational waves by Dr. Alex Kann, or Dave, as we like to call him. Dave obtained his diploma in 2004. Both his undergraduate and his PhD were both done in Germany. 2004 was at the Friedrich Schiller University in Jena. Excellent. And his PhD was obtained in 2011 in Teutoburg, where he continued as a postdoc until he joined us earlier this year, February, March, as a Juan de la Cierva postdoc fellow. And he's involved with research mostly of gamma ray bursts. He has a lot of highly cited papers about samples of gamma ray bursts, mostly their afterglows, looking at their statistical properties. And he was also involved with a recent GRB supernova, a very famous, a very intriguing one that I discussed last week, which was associated with an ultra long duration GRB, 2011 1209. Right? And it's supernova 2011 KL. I think that won't be the topic today, but instead about gravitational waves and kilonovas. So thank you very much, Alex. Good luck.
Yeah, so welcome everyone. All of this is essentially one single source with multiple different designations, seen not only in different wave bands of the electromagnetic spectrum, but actually with different so-called messengers. So not just electromagnetic radiation as we're used to, but also and especially in gravitational waves. So gravitational waves are a topic which would fill at the very least an entire seminar by itself if you wanted to talk about it in detail, or maybe even an entire book. I'm just going to say a few short things about it. So Einstein in 1916 already predicted from his general theory of relativity that that accelerated masses should create deformations in space-time, which then propagate outward at the speed of light, at least according to general relativity. And these gravitational waves are emitted by any mass which is accelerated. So if I punch my fist, I am emitting gravitational waves. But on the other hand, the coupling between these waves and the matter of the universe is extremely small or weak, which means that it is extremely hard to measure them. And I am reasonably sure that even in the far future, my fist punching will not be able to be measured by anything. But of course, there are other sources in the universe which have to do with accelerating masses, which are a lot larger than my fist. And the most important things here are the coalescence of compact objects, be they black holes, neutron stars, or black holes and neutron stars together, or the core collapse of supernovae. So, how do we actually detect these gravitational waves? This has been a project which has been ongoing for nearly 50 years, starting off with people like Max Weber and large cylindrical detectors, which allegedly already detected gravitational waves shortly after being built, but this turned out to be noise sources. But by now we know that gravitational waves really do exist and can be measured, and absolutely instrumental in this were the LIGO detectors, which stands for Laser Interferometer Gravitational Wave Observatory. And these are two detectors. This is a picture of one. I think this is the one in Hanford, Washington, in the United States of America. The other one is in Livingston, Louisiana, which is surrounded by a lot more forest. And as you can see here already, this is for the most part an overgrown detector consisting of two arms that are orthogonal to each other. And the very general principle is that a strong laser is injected into these two arms. There's a beam splitter sending part of the beam along each of the arms. Finally, to test masses, which are highly reflective and extremely well suspended mirrors. And these reflect the beams, send them back, where finally they are detected in a photodetector. And as assuredly everyone here knows, if you combine two lasers together, you will get an interferometric signal of stripes, dark and light stripes. And if you jiggle this apparatus and change the length of the arms, you will get moving interference patterns from amplification and destruction. And in this case, what they actually do is adjust the arms in such a way that there is a very small interference pattern visible, and if the arms get moved in some form or fashion, this pattern will change either into zero or maybe become stronger, and by this way they can measure the gravitational waves. So the technology behind this is again another entire seminar. So it's really highly interesting what they have done, like especially when it comes to the suspension of the mirrors, the way they cancel out all kinds of anthropogenic and natural noise. So they can basically measure trucks passing by miles away. They can see people's footsteps in the whole system and everything. So and as you can see here, where the two detectors are localized in the United States, so they are quite far apart. The light travel time between them is about 10 milliseconds, and this can be used to do interferometry and to measure the location of the gravitational waves in the sky. And furthermore, what is not seen here is that there is a third detector in Italy, which is called Virgo, which has also, as I will mention later, gone online recently in its advanced state. So, we do know that gravitational waves exist. Indirect measurements have been done since the late 1970s with the so-called Holtz-Taylor pulsar, which is a binary neutron star in which both neutron stars are pulsars. So their signals can be measured with extremely high precision with radio telescopes, and it has been found over the course of the last 40 years that the orbit of these two pulsars is shrinking, and it is shrinking exactly according to the predictions of general relativity, in the sense that they are radiating off gravitational waves as a constant source and are therefore slowly losing orbital momentum. But this system is not detectable by current detectors. What we do have, though, is gravitational wave 150914, which actually occurred on the birthday of Dr. Deogate Postigo, so he's very proud of that. And this was a very powerful black hole merger, which was interestingly detected even before the very first observation run started, which caused, it seems, a lot of excitement and consternation back then, because a lot of people were not sure if this was actually a so-called injected signal, where humans in the loop, like a small elite cabal of people who know about this, do false triggers to test the system and the reaction of other people. But yeah, this was actually turned out to be real. And interestingly enough, this source was actually composed of two very massive black holes. So if we think of stellar black holes, stellar mass black holes, you usually think of things in the range of 5 to 10 solar masses, and these had over 30 solar masses. And they merged together to a combined black hole of over 60 solar masses, and thereby radiated 3 solar masses in a very short time in pure gravitational radiation. The signal to noise, I've just thought this might be interesting of this source in both detectors combined, was 24, which is extremely high. And one thing I can't really explain to you, but it is possible out of the waveforms and the ring down, it can be measured what the distance of this source is, though the errors are relatively large. And you can see it's about 440 megaparsecs, which is roughly a redshift of 0.093. So for us gamma ray burst people, this is local universe. For other people, this might be very far away. But anyway, this was within the predicted horizon of the LIGO detectors for detection. And interestingly enough, this source remains up to this day the loudest black hole merger seen so far. And the problem here is that if you only have 2 detectors, you will roughly get a so-called annulus for the error box. And in this case, it's usually called a banana. So what you can see here, these are some slightly different maps depending on which analysis routine was used. You can see that there's a very large region covering much of the southern hemisphere and also, at lesser probability, parts of the northern hemisphere. And the entire region has more than 600 square degrees and is obviously not accessible by a single telescope from a single site. But of course, since this was the very first case of a gravitational wave, it triggered a very large follow-up campaign with a lot of telescopes doing tilings of these error boxes, and all in all, nothing was found. And, well, it's not true to say that nothing was found. Of course, in such a follow-up, there will be a lot of new supernova discovered, and in another gravitational wave, which I'm otherwise not going to mention here, which happened in January this year, for example, the afterglow of a Fermi gamma ray burst, which had not been seen by SWIFT, which was not localized well, was discovered purely by chance within the error region of this gravitational wave, but it's 100% clear that the two sources are not associated with each other. And of course, if you have such a huge error box, which look essentially similar for this one, the chances of maybe finding one GRB afterglow are not so bad. And one point is that for the merger of gravitational black holes, you would not really expect an electromagnetic signal. So to get some kind of electromagnetic radiation, you have to involve matter, and simulations of black hole mergers show that even if both black holes are surrounded by accretion disks, these will get destroyed relatively shortly before the merger, and in the end you basically have the black holes spiraling together in a very hard vacuum. And while there have been a lot of theories how it might be possible to somehow still get magnetic fields or so out of that and maybe accelerate electrons to create synchrotron radiation, the general simplest theory is that these things will emit large amounts of gravitational waves but nothing else. So all in all, this yielded some very interesting results, but if I might say, wasted a lot of telescope time on optical facilities. And it has been visible that the further we get on with the detection of black hole mergers, the less follow-up is actually being done for them. So there was one case which is relatively recent, which I am mentioning here because for the first time it has an error box which is significantly smaller. So the Virgo detector, which I had mentioned beforehand, went online in its advanced state only on the 1st of August of this year, and the entire O2 run only went to the 25th of August. So there was only about 3.5 weeks where all three detectors were running at the same time. And luckily enough, just 2 weeks after going online, another very powerful black hole merger was detected. And as you can see here, the Virgo is not as sensitive as the two other detectors, but there is still a clear chirp signal in here. And you can see here, this is not very strong, but it's definitely detectable. And this led to an error banana, in this case from the LIGO detectors, and then the final one from the Virgo detectors, which was significantly smaller in about 60 square degrees, which for optical follow-up is still quite problematic, but at least it can be handled from a single telescope, from a single site, in the sense that you have a relatively small portion of the sky which can be observed. 3 days later, so I'm not really sure about any optical follow-up of this source. I guess there was a little bit, but 3 days later all of this was interrupted and dropped because we got this guy. And this is, as Zach already said last time, the main topic, the centerpiece of the focus. And as you can see here, just maybe to go back, this is what a black hole merger looks like. You have a relatively, oh, this is very small. This is actually just in the range of hundreds of milliseconds or even less, the signal that you can see from the black hole. Zach?
Do you recall the masses of this one?
I
don't remember off the top of my head.
Actually, yes, I kind of mentioned it here. So they were a little bit less. I think the combined mass was like 52 or 50 solar masses. They were a little bit less than 150914, and it was also a bit further away at 550 megaparsecs. So that's why the signal is all in all a bit lower. It's still a signal to noise of 18, which is still quite good, but it wasn't quite 150914. Anyway, and I hope this is reasonably visible here in the plot, especially from Livingston, where you can see this is 30 seconds here. And actually, I've read different numbers. So certain sources say that the signal was seen for 60 seconds. Some say it's seen for 100. Some for even more, like 5 or 6 minutes. So I'm not really sure what the exact number is. Another source stated that the whole thing can be seen for about 3,000 revolutions before the final in-spiral. And this is the very first binary neutron star in-spiral ever measured. So the fact that the masses of these sources are significantly smaller than in the case of the large stellar mass black holes leads to the entire in-spiral to be slower, and you get a signal which ramps up for a long time before it finally crashes together. And one thing you can probably even see from there is that in Virgo there's actually nothing to be seen, which is peculiar, because the source was more than bright enough to be detected also by Virgo. And initially when I heard about this, I was very puzzled, because gravitational waves basically can't be shielded. But it turns out that these detectors, due to the fact that they have these orthogonal arms, have blind spots. So if a gravitational wave comes from a very certain direction, the change in the length of the arms is going to be basically exactly the same, and the detector is not going to see anything, even if the gravitational wave is very strong. And in this case, the fact that it was lying in a blind spot was kind of fortuitous, in that it helped yield a very small detection region, which I have not mentioned here yet. I will come to that in the next slide. And in this case, it actually turns out that because the whole thing is a lot more messy, because matter is involved, it is relatively hard to pin down what the actual component masses are. So a rough estimation is that one of them was about 1.2 solar masses, the other 1.6 solar masses, whereas the combined mass of 2.74 solar masses is well measured. And one thing that is unclear is what actually the fate of this merger was. There are certain indications that it did collapse very shortly after the merger into a black hole, in the sense 30, maybe 50 milliseconds later or so, but I don't think there are any certainties here. So, now, the really, really interesting point is, I mean, it's nice enough to get our first binary neutron star in spiral, but 1.74 plus minus 0.05 seconds later, the Fermi GBM triggered on a short gamma ray burst. And in terms of gamma ray bursts alone, this was a pretty weak source. The localization had an error of over 11 degrees radius, and if there hadn't been a gravitational wave signal right beforehand, no one would have been interested in this thing. No one would have followed it up. But this was actually the very first signal which was sent out to the world about 25 seconds after the burst. The signal was received on Earth as a trigger from Fermi GBM, and later on inspection of the anti-coincidence shield around the spectrometer board integral showed that it was also seen as a 100 millisecond spike. This was too faint to actually cause an onboard trigger, but the perfect coincidence in time with the GBM event means that this is also the signal of this short gamma ray burst seen. And as you can see here, it's obviously there's a time lag between the two, and this is in different energy bands. So this is a relatively soft band, 10 to 50 electron volts, and this is 50 to 300. And you can see there's a relatively hard short spike, and then there's some emission that comes afterward. And later analysis showed that this burst was too faint to trigger the CONUS detector on the WIND satellite, and since the CONUS detector in the so-called waiting mode only accumulates data up to about 3 seconds each, such a short signal would be washed out, so it was not visible. And of course the perfect satellite to detect this would have been a Swift satellite with the Burst Alert Telescope. which would have had some very interesting consequences, because then everyone would have immediately had an error circle of about 3 arc minutes to look for any kind of sources instead of 26 degrees, but this didn't happen. It was outside the field of view. Maybe even Swift was on the wrong side of the Earth, I don't know right now. Anyway, so it's already interesting enough that you have a gravitational wave and a short gamma ray burst happening at essentially the same time. And there are some quite nice papers that have been published in AppJ Letters on the combination of these two events alone. So here's an analysis of the duration of the source, which comes out to be at 2 seconds in total from Fermi. And this is this classical long-short divide, which is actually detector dependent. And in this case, they find out that the probability of it being a short burst is about 73%. And this plot here shows, again, the duration versus the so-called spectral hardness, which is just the fluence in 2 predefined bands compared to each other. And maybe, hopefully you can see it here. This is the small spot. So it's lying roughly between the definite long bursts and the definite short bursts, and it's maybe a bit on the soft side. And the interesting thing is that, as I had shown here, in hard radiation you have this relatively short spike, and then you have this little bump afterwards, which is temporarily most of the emission. And the Fermi GBM team actually found out that this is best fit by a thermal spectrum. And this is relatively peculiar, but let's say it's still not absolutely extraordinary. So the nice thing is, as I mentioned, the non-detection in Virgo allowed this source to be localized very well, and here you can see several error circles. So if you just take the 2 LIGO detectors alone, you once again have one of these bananas which show up on both hemispheres. Then you have the very, very large error circle from Fermi, which is over 1,000 square degrees. If you compare the timing of the arrival of the short gamma ray burst in integral and Fermi, you get this extremely wide annulus, which is not really helping anyone. But if you then combine the whole thing with the Virgo detector, you get this relatively small error region of about 28 square degrees. And the really interesting point is that I had mentioned beforehand that you can derive a distance out of the gravitational wave signal itself. And this distance is, in this case, 40 plus 14 minus 8 megaparsecs. And this really is local universe, and represents, with just a small margin, the second closest gamma ray burst ever discovered, by far the closest short gamma ray burst ever discovered, and was critical in detecting an optical counterpart. So one thing I should mention is that the fates were not very kind, smiling upon us when it came to optical follow-up. The source was not very well observable. It was pretty much impossible to see from the northern hemisphere, which is the reason why we couldn't get any GTC observations of it. So it was mostly confined to Australia, South Africa, and especially, of course, Chile. And it was only observable for about 1 hour after nightfall, right after the gravitational wave happened, and a month later it became completely observable because it was moving behind the sun, even with NIR detectors. And at the moment, the only thing that can observe it is radio telescopes, but roughly at the beginning of December, everyone is going to start looking at it again. And here's a little plot which just shows a timeline and the air mass of the source from South Africa, Chile, and then later on Australia. And as you can see, here is already something about counterpart announced. So the question is, how do you follow up something that is still only localized to 28 square degrees? There's basically 2 kinds of techniques. The first one is a tiling approach, which is roughly the same thing that I had showed originally already with GW 150914. And this just means that you take some kind of detector which has a field of view of several square degrees, and you just start shooting at the entire sky. And this is, for example, in this case, what was done by the dark energy camera on the 4-meter Blanco telescope at CTIO. They have a detector with a very large field of view, and you can see each of these red, roughly circles represents a single image, and they just started tiling the whole thing. And here you already see an orange dot, which is nice. And the other way to do it is actually even more interesting, and this was actually proposed by none other than Neil Gehrels, the former PI of the SWIFT mission, who has sadly passed away last year in, I guess, maybe his first author paper. And that is to use the distance information that you get from the gravitational wave signal to do a pointed approach looking for galaxies which not only lie in the two-dimensional spatial error region, but in the three-dimensional spatial plus distance error region. And for this, people have been creating catalogs with distance information. For example, one of them is called GLADE, which is the one that was used here. And people have created programs that within seconds can spit out a list of targets with thumbnails and certain criteria to sort them. And in this case, there was one team, the so-called 1 meter 2 hemisphere team, which was using the 1 meter SWOPE telescope at Las Campanas Observatory in Chile, and with something called the SWOPE Supernova Survey, and they targeted a bunch of galaxies here in the arrow circle, and number 9 on their target list turned out to be a large elliptical galaxy from the NGC catalog. And in this catalog, they discovered a little point which had not been there before. Now, of course, this doesn't have to be anything special. This could be, say, a type 1a supernova. They relatively quickly found out that the luminosity was under that of typical type 1as, but maybe if it's a type 1a discovered early, it could fit. And there were multiple other teams that were all using telescopes located in Chile to observe this region. So there were in total there were 5 different teams which actually discovered this source completely independently of each other, in the sense that they had actually registered that it existed before the GCN from Kulte et al. Came out reporting the source. And finally, also a team that we have been involved in, which used the Wide Field Vista telescope, which is close to VLT, to also detect this source in the near infrared. But they actually only saw it. So they took images before the source was announced, but they only saw it after the announcement, and they just went looking and said, oh, we see it as well. And the interesting thing is the source had a magnitude of about 17, which is actually, as Zach mentioned last time, still in relatively easy range of amateur astronomers with a bit too much money. So if you have a 12-inch or maybe a 20-inch telescope in your backyard, you can observe a gravitational wave electromagnetic counterpart. Yes?
So how come there was an image of this galaxy before? Was that just by chance, or?
Well, like I said, this is an NGC galaxy.
Oh.
So first of all, obviously, it's going to be very well visible in the DSS. I think there's Pan-STARRS coverage, and there's actually one team which is called DLT40, which is interestingly enough stands for distance less than 40 megaparsecs, which had actually imaged this source about 20 days before the galaxy, 20 days beforehand, just by chance, because they were going through all of this galaxy catalog, just checking. And of course, there's no source visible at that time, down to something like 3 magnitudes deeper than the magnitude when it was discovered. And as soon as this thing was announced, it obviously led to an absolutely gigantic follow-up campaign. And so one thing is, it's a bit peculiar that I'm the person doing this talk, because out of our group, I'm the one who was actually involved the least in all the observations for certain reasons. And just to share a slightly personal story, I had, at the day of the gravitational wave, I had sent around to my colleagues, oh, here's something the gravitational wave found, strong signal. And a few hours later, the first GCN came out saying that was a binary neutron star merger, and Zach was sending us the GCNs because we don't get them. And then we went to bed, and the next morning Zach sent out like 30 GCNs because everything was just completely exploding after the source had been found. So here's another thing I could talk about probably for 20 minutes if I wanted to in a galaxy seminar or so, about the NGC galaxy. So what you can see here is basically a blob. This is an S0 lenticular galaxy with a very low star formation rate. And the distance of this source, and this is what I think is one of the most fascinating things, is about 42 megaparsecs. So the distance measured from the gravitational wave alone was perfectly spot on, even within the relatively large error bars. And actually the distance to this source is moderately not well known. There's a complete paper by Jens Hjort discussing different methods to determine the distance independently from simply the redshift. And this number measures somewhere between 39 and about 44 megaparsecs, depending on which distance indicator you actually use. And there's some things that aren't really visible here in these images, but there are some indications that there has been a so-called dry merger in this galaxy, and there are some dust lanes which form an interesting warped spiral pattern, and some emission lines that are visible. There's a Muse paper by Andrew Levan, which nicely shows these things. And the source we are talking about, which was later called AT2017 GFO, as Zach already mentioned last week by the IAU, is located relatively far outside the center of the galaxy, very roughly at the half-light radius. And the core itself is a low-power active galactic nucleus, which is nicely visible in radio and X-rays. And all in all, this seems to be a very typical host galaxy we would expect for a short gamma-ray burst. So this is clearly not a galaxy in which you would expect a long gamma-ray burst or a type 2 or maybe type 1bc supernova, because there's no active star formation.
Sorry.
Yes?
If you go back to the previous image, you can see the evolution of the kilonova from the white.
Yeah, it's not very well visible. So this is an image from beforehand, where there's nothing, and then you see this blue source here, and then later it becomes red, which is something I will mention in more detail in the next slides. I had actually asked Niall to maybe put these three things below so that you can see it a bit better, but that comment was ignored. Anyway, so just as a first example of of a light curve with just a few data points, what you can see here is interesting in the sense that this source evolves much, much more rapidly than any known kind of normal supernova. So here's just typical light curves for type 1 and type 1bc supernova. I guess these aren't GRB supernova because they're quite a bit fainter than the type 1a. And also, I think these two are so-called type 0.1a supernova, which is a special class in which if I remember correctly, the white dwarf is not completely destroyed. So they have very fast light curves. And as you can see, this source here decays much, much more rapidly than anything known. And I think this is R band. In the ultraviolet, the decay was even more fast, as you will see in the next slide. And only in the near infrared, it took a lot longer and was a lot more stable. And this means that the color evolution that the source exhibited was also extreme, which is already one interesting point in the sense that it does not resemble the afterglow of a short gamma-ray burst, because afterglows usually have none or small amounts of color evolution over time. But all of these properties are those expected from a so-called kilonova. So now I should say, what is a kilonova? This, again, is a topic that a lot of time could be used to talk about. Let me quickly say something. It is something roughly similar to a supernova in the sense that you have ejecta involved, which is emitted outward at very high speeds, and you have radioactive elements. But instead of having large amounts of nickel-56, as in both type 1 and type 2, supernova, what you here have is heavier elements from the so-called rapid process. And the rapid process is a nucleosynthesis process in which elements, relatively light elements up to iron, are turned into elements all the way up to uranium and possibly even higher by the very rapid accumulation of neutrons within very dense neutron-rich matter, in the sense that the accumulation of neutrons is a lot faster than the radioactive decay of the actual mostly unstable elements. And originally, it had been thought that this rapid process would take place in the core collapse of supernovae, but in recent years it has been found that this is probably an inefficient process in supernovae, and the theory came up that the mergers of neutron stars might be the main source of these R-process elements. And in one of the papers I read that actually some milliseconds after the merger, you would get a source which roughly has the size of our sun and a density which is at least that of the mean density of the sun or even higher. And in these conditions, you can form this rapid synthesis of elements. And these are just some theoretical light curves, and this here shows the fraction of the so-called lanthanide elements within the ejected matter. And if this fraction is very low, you are going to get a bright, fastly evolving so-called blue kilonova. And if the lanthanide fraction is significantly higher, the evolution of the entire thing is going to be a lot slower, and the source is going to be a lot redder. So Zach mentioned last time already that there has been one short gamma ray burst where evidence has been found of a kilonova, in the sense that you had an optical afterglow. You could determine an extension of the optical afterglow to late times, and at late times there were two data points. One of them was an optical data point, which was, I think, just a little bit less deep than where the afterglow should be, and the other one was a much brighter data point in the H band, which showed that the source had strong color evolution, and this was seen as the evidence of a kilonova, though we really had no light curve, just a single upper limit on the color, or no, lower limit on the color, and that was it. And on the right hand here you can see some predicted spectra of what the source should look like at different lanthanide fractions, and additionally there's a strong dependence upon the ejecta velocity. And as you can see here, the higher the velocity gets, this is 30,000 kilometers per second, 60,000 kilometers per second. So this number of 0.1 c is the typical ejector speed of broad-lined type 1c supernova associated with long gamma ray bursts. This is twice as much. And you can see here that all of these sharp absorption lines get completely smeared out. And that is one way to measure the ejector velocity, but it also complicates a lot of things because all your absorption lines just run together.
These are still different fractions as well.
Yes. So the colors are the colors are the different speeds, and the two panels are for the blue kilonova and the red kilonova. So one of the points about this event has been that, due to the extreme amount of follow-up and the large amount of groups that have been working on it, there are something like 5, maybe 6 different topics on this event, which are in most cases covered by very many papers, and if you start reading them, they basically all just say the same thing, depending on how much data they have. And just yesterday morning, so I'm maybe going to step on some people's toes by not mentioning all of them, but yesterday morning there's one group which is associated with the group of Edo Berger, which compiled the entire data set as it has been published so far, which is probably most of it. And they filtered the whole thing for outlier data points. They shifted a bit depending on how the things are calibrated and everything. And then they started fitting analytical kilonova models to this large data set. And here you can see this extreme color evolution. So this is ultraviolet data from the Swift telescope, which just drops into oblivion. Here's one single very, very faint data point obtained by the Hubble Space Telescope in roughly the U band. And this goes all the way to the K band, where the evolution of the kilonova is relatively slow and shows a plateau phase up to about a week after the gravitational wave, before it then starts dipping and then becoming less steep again. And yeah.
What were the lines?
So the lines here are the expected kilonova models, and that's what I'm getting to here in this plot. So this is the whole thing shown for the different filters, starting with the ultraviolet W2 filter going all the way to the K band. And what they have done is they have not fitted a blue or a red kilonova to the data, but they actually did a 3-component fitting, which one could call a blue-purple-red kilonova. And in this case, it means that the ejecta of the kilonova is extremely asymmetric, and depending on the direction compared to the original in-spiral, you not only get different ejecta speeds, but you also get a different lanthanide fraction. So on the one hand, you have polar ejector, which is basically moving vertically to the what's it called? The ecliptic of the system, and which is roughly similar to a gamma ray burst, which is emitted along the poles. And this ejector is very fast. I think they find about 0.2 light speed, and consists mostly of relatively light elements. So it's our process elements beyond the iron group, but not the very heavy ones. And then you have some kind of transition between the two, and finally along the equatorial plane, you have the slower red kilonova, in which the large lanthanide fraction leads to very strong absorption in the optical, which creates this extremely red emission. And I did not get around to reading the paper, so I don't have any big details or so on it, but this, I think all in all it seems to be a good fit. And so here you can see the blue, the purple, and the red are the three different components, and the black is added together. And all in all, it's quite interesting. I think there's this very short peak at early times at roughly 1 day, which almost in all cases systematically lies above the extrapolation, above their fit model, but otherwise it fits very well. So, the fact that this was a 17th magnitude source and was visible from a lot of big telescopes led to an absolutely fantastic spectroscopic follow-up campaign. So this is some Gemini data and mostly VLT X-shooter observations from the paper by Elena Pian in Nature, which go all the way into the K-band. And the main takeaway here is that there's not very much seen in the optical up to about 8,000–9,000 angstroms, but once you get into the infrared, you see these very deep and broad absorption lines. So these spectra, at first glance, if you ignore the wavelength scale, have a certain similarity to broadline type 1c supernovae, very roughly speaking, but then you see that the whole thing, instead of taking place in the optical, is all in the infrared. And here's another Nature paper, one in which Zach is also co-author on, from Stephen Smart. And this shows some more spectra in combination with the spectral energy distribution. I think these data are almost all from Grant. And here's some, I think you already showed this plot last time, right? Some first tries of modeling the absorption lines of the kilonova with our process elements, in this case cesium and tellurium. And this is something which is, has only just begun, so I'm pretty sure there will be a lot of papers on this in the future, on the spectroscopic data set, because in this case the observations just zoomed past the theory. So I mean, there are a lot of kilonova models, but they are not very refined, because especially the details in terms of the absorption lines by the different elements are extremely hard to compute. So this is work for the next probably decades. And the very, very main point, at least according to the news media after the big announcement on the 16th of October, is somewhere out there there's something which is producing many Earth masses of gold and platinum. So we should go out and mine it. And okay, so probably the thing that I have the most slides on is the fact that, coming back to the gamma ray burst, this is a source which is seen so-called off-axis. I will talk about what off-axis is soon. And these are some further images from Nature and Science papers. The source, as has been shown, was very bright in the optical initially and also later in the near infrared. It was an extremely bright gravitational wave. It was a pretty faint but detectable gamma ray burst. But in all other electromagnetic wave bands, it was extremely faint to non-detectable. So at very high energies from satellites and also ground-based Cherenkov detectors, nothing was seen at all. And in the X-rays and the radio wavelength, nothing was detected for in between about 1.5 to 2 weeks. And then the source slowly started to rise. And this is a Chandra image, which shows nicely the core of the galaxy, which is also seen strongly in radio. As I mentioned, it's a low-power active galactic nucleus. And then here, this source popped up after about 9 days. And there's actually a very deep Chandra image 2 days after the gravitational wave, which shows nothing at this position. And this is very untypical for a gamma ray burst. A gamma ray burst you would expect to be very bright at early times and decay later, and maybe in the radio it would take a rise time of about 1 or 2 days before it starts decaying, but this thing should have been seen. But this very late detection of what is likely the afterglow is the signature of an afterglow that is off-axis. So here's some more slides showing just how faint this thing is compared to the known sample of gamma ray bursts. So this is from the paper that I actually did the most work for, which was led by the team using ALMA, Sam Kim, Steve Schulze et al. And this plot is actually from Antonio de Ugarte Postigo, which is a collection of both millimeter, submillimeter, as well as radio detections, or in this case also upper limits of GRB afterglows. The red ones are short bursts. As you can see, there are some radio detections of short bursts, which are mostly fainter than the long ones. In millimeter, the short burst has not been detected at all yet, but the upper limits, or the faint detection for this source, are orders of magnitude beneath what we know so far, yes?
Is this for a given time after the explosion? Like 1 week, 1 day?
That's actually a good question. I guess it's, I don't know, I'd actually have to ask Antonio when it was done. It's possible that this is just like, always like maximum measured, something like that. I'm not sure. I mean, in X-rays or optical, it's usually relatively easy to pin it down at like 1 day because you're going to have early observations. And these observations are usually more sparse, so I'm not sure. And another plot from this paper, which first of all shows X-ray light curves. So for long GRBs, there are so many that we just did this probability, this fraction plot. The blue curves are short GRB afterglows individually, and this down here are the measurements for GRB 1708, 17A. Here's this very deep Chandra upper limit. These are less deep upper limits from Swift follow-up, and then finally some detections by Chandra. And as you can see, again, orders of magnitude difference. And additionally, if you look at the isotropic energy release in gamma rays, you have in gray here the long bursts and the short bursts, which already show that short bursts are significantly fainter. This is well known. And then here you have the green stripe of GRB 1708, 17A, again, orders of magnitude fainter. So the explanation, likely explanation for this is that we were not looking pole on at this source, but at an angle. And I'm not going to go into deep details here, but these are different kinds of models for GRB jets. And if the viewing angle is off-axis, it implies that at early times the collimation of the jet is so high that basically all of the radiation is beamed past our line of sight and we don't see anything. And then later on, when the jet becomes decelerated in the interstellar medium, the opening angle goes apart and we finally start seeing parts of the jet. And there is one model which I think is favored right now, is that during the coalescence of the two neutron stars, there's additional emission from a very hot cocoon, and that possibly this is what we are seeing as the prompt emission of the gamma ray burst. There was also a paper from, I think, just this morning, which was talking about the possibility of having radiation from the actual jet scattering into the cocoon, and then that is what we are seeing. And here again from the paper by Kim, Schulze et al. This is modeling in different wave bands from X-rays to ultraviolet and optical, and then in different millimeter and radio bands. So these are ALMA upper limits from our paper. And here there are also some detections at 6 and 3 gigahertz from VLA and ATCA, which show the evolution of such an off-axis afterglow, which, as you can see, so this is about a bit more than 1 day. This is 1.5 weeks. You can see is basically completely invisible right after the burst, and then slowly rises and finally is able to be detected in both X-rays and radio. And these other thin lines are predicted emission in these different wave bands if the thing were seen on axis. So actually, if this burst had been on axis, it probably would have been one of the brightest gamma ray bursts ever detected. And would also likely have had an extremely bright optical afterglow, even though it's just a short burst, which would have meant that the kilonova itself would have been quite hard to detect. So at least for kilonova physics, it was very lucky that we were not looking right into the throat of the gamma ray burst itself. And there are also some predictions we make in this paper about the peak energy and spectrum of the on-axis burst. And I'm also thinking of studying what the optical emission would look like in an on-axis case. Okay, finally something almost completely different. I don't know, did you also show this?
No.
Oh, okay. So this is actually an interesting paper also published in Nature by the LIGO team together with a bunch of optical follow-up people. And as I mentioned beforehand, it is possible to derive distance completely independent of any other distance indicators from the gravitational wave signal itself. And if you have a distance and then actually find the optical source and are able to measure the redshift or use other distance indicators to determine the distance to the source, you can determine the Hubble constant out of these measurements. And what we see here is the interesting fight that is going on right now between type 1a cosmology, which is here the so-called Hughes sample, which was published last year by Ries et al. And this titer limit here, or this titer measurement here is from the Planck satellite. And these two measurements are in this, there's a certain discrepancy between them. And the gravitational wave detection yields a measurement of H2 with a very large error bar of something like plus 20 minus 10 or so. So it hardly can be used right now for independent cosmology, but the interesting point is that the central value of the measurement falls exactly on 70 kilometers per second per megaparsec, which is a nice result. If it were like 30 or 150, you would think like, something's wrong with the method, but it's working out quite well. And so of course this is a case where many more detections are needed in the future to reduce this error bar. So, finally I want to talk a little bit about what you might call a meta topic, not so much on the event and the science it delivered, but on the science of the event, in the sense that the resonance of this event was absolutely incredible. So it was the press conference was a few weeks ago on the 16th of October. And at the moment that the press conference started, already 23 papers were published in one fell swoop in a special edition of the APJ Letters, and at the same time preprints of 7 papers in Science and 6 papers in Nature were put online. And at least in terms of gamma ray bursts, I'm reasonably sure that the most high impact journal papers for a single GRB were for 990123 with 3 each. And this is a total of 13 in the 2 journals. And of course then the physical review letters paper from the LIGO team on the actual gravitational wave, which in the short 2.5 weeks has already gotten over 50 citations, I should mention. And then in the evening, the archive listing came out for the weekend, which contained not just archive versions of these 37 papers, but in total 76 papers on a single event. And it was nearly 200 papers on that archive listing, which is probably also a record. And I actually saved the page just for historical reasons. And by now over 100 papers on the event have been published. And I was thinking if there was any other event in astronomical history which was in any form or fashion comparable. So that definitely this is way more papers than, for example, for the first gravitational wave detection of the black hole merger, which produced, I think, like a dozen papers or so on the first day, and quite a lot more by now, probably 100 or so, but not within 2 weeks. And I actually did, I asked some people on the forum, shout out to a certain stupendous man on cosmoquest.org, who's been an astronomer for a way longer time than I have, and he told me that he had done a bit of research and found that within 2 months there were 69 peer-reviewed papers published on SN 1987A, so this is pretty much comparable. But I think this is the only event in astronomical history which has produced such a resonance. And finally, there is a paper, the first one in the APJ Letters issue, which deals with the dawn of multi-messenger astronomy, so the first time that truly an event has been detected not just in in all the broad forms of electromagnetic radiation, or maybe in only neutrinos also, or only gravitational waves, but in two completely different messengers at the same time. And of course I should point out that as in 1987, A also had the famous neutrino detection, but if I remember correctly, this was only found days later when people actually started looking into the data, whereas in this case, everything happened very fast. And this paper is probably going to become both famous and infamous. It is in APJ letters and is 59 pages long, and over half of that is just the author list of nearly 3,700 people, because this paper contains everyone who has published any other paper in the first wave, or at least of observations. And it is estimated that this comprises 1/3 of the entire astronomical community, which I guess is, at a rough guesstimate, 10,000 people worldwide in all fields. So either you're on it or you're not. From now on, this will be the discerning criterion. And as my last slide and something of a summary, I will point out some of the highlights from the different discoveries. So I missed something. I actually wanted to put, this should have GW 150914 and GW 170817 on top. So for the first detection of gravitational waves, what did we learn? First of all, direct evidence for the existence of gravitational waves, which was, people were pretty sure they existed beforehand from the Holtz-Taylor pulsar, but it's always nice to see something directly. Secondly, I remember about a bit over a decade ago, some person published a paper claiming that certain effects of quantum space-time would lead to a damping of gravitational waves over long distances, and his prediction was that gravitational waves could not be observed because we were basically looking through a thick fog, and obviously this is not true. It actually seems that space-time is completely frictionless, especially from the comparison measurement of the distance of the gravitational wave from the neutron star in spiral compared with its actual distance, which fits perfectly. Furthermore, we finally got very direct evidence of the existence of stellar mass black holes, so the evidence for supermassive black holes at the centers of galaxies is pretty much irrefutable by now, but for stellar mass black holes, there was a lot of indirect good evidence, but nothing direct. And interestingly enough, it turns out that there are stellar mass black holes which are significantly larger than most models of stellar evolution predict. Furthermore, the gravitational wave signal looked exactly as general relativity predicted. And finally, on the technological level, it was a proof of concept that laser interferometers work like they should. And especially, I personally have to say, after many years of non-advanced LIGO finding nothing, I was very pessimistic that any upgrades would discover anything, so I was quite happy. I'm especially happy that I didn't do a bet on it, because I would have lost. So, and now the question is, which of these two was actually more important for astrophysics? And I guess I'm biased, but this list is longer. So first of all, probably the main point is that we now have absolute smoking gun evidence that binary neutron star mergers are the sources of short gamma ray bursts. Again, there was a lot of circumstantial evidence beforehand, from the galaxies that they were happening to the distribution of offsets to galaxy cores and other things that pointed to binary neutron stars, but now finally we have the proof, if you might call it that. Furthermore, this is the very first time that there is very clear proof of the observation of off-axis GRBs. Obviously these things have to exist, but we now have something to play around with. One thing I didn't mention beforehand is that there are some interesting inferences on the speed of light versus gravity. So we have a 1.7 second delay between the gravitational wave and the GRB. This can be due to multiple reasons, but if you assume that for whatever reason both of the events happened at exactly the same time in the source frame, which is very likely not true, but then you still have an upper limit of just 1.7 seconds between the speeds over a distance of 40 megaparsecs, which leads to some very strong constraint about quantum gravity theories.
In that case, you say the gravity is faster than light?
Well, yeah. Yes. Well, yeah, that's why I'm saying it's very unlikely that the 1.7 second offset is a true phenomenon of space-time.
Or can it be that something slows the gamma rays?
Yeah, it would more be that there's some kind of very slight breaking of light.
Or maybe he just takes out one for the jet before.
Yes, yes, that is very probably the reason. There are you can derive new results on the binary neutron star merger rate. And one thing that we already pointed out last week is the fact that this source initially had 17th magnitude in the optical, and something like that is easily detectable by one of the many wide field tiling surveys that are going on today, like the Intermediate Palomar Transient Factory, MASTER, and ATLAS, and other surveys which are producing large amounts of supernova discoveries, and this would be completely in their range. But no one has ever seen anything like this independent of a GRB or gravitational wave beforehand. And one thing I actually wonder is if you look at like the astronomers' telegrams of spectroscopic follow-up of sources detected by Gaia and other transient surveys, every once in a while you find something which is like 17th, 18th magnitude at discovery, and a week later they looked with a larger telescope and they simply found nothing at all and couldn't take a spectrum. And there you kind of start to wonder, well, maybe, who knows, maybe that was a kilonova that people just missed because people usually don't do follow-up in the infrared for unknown sources. Furthermore, there's now absolutely excellent evidence for not only the existence of kilonova, but also linking them to short gamma ray bursts, again, something that was expected from the standard models, but now we have the evidence. There's very strong evidence that binary neutron star mergers are perhaps at least one very important, perhaps the most important source for our process nucleosynthesis in the universe. There's the possibility of using gravitational waves as a new cosmological standard siren, and something that will probably also be studied further in the future by a lot of papers are inferences on the neutron star equation of state, the properties of hypernuclear matter and things like that, and a lot more things that other people will have to come up with. So, thank you for your attention. I will leave you with this little comic, which has actually been created by one of the members of the LIGO team itself, who has a webcomic, and it's probably too small to actually read on the screen, but yeah, whatever. So if you have any further questions, please ask.
That the fact that Virgo didn't detect the event meant a better location estimate, but how do they know that Virgo didn't detect it because it was in the blind spot and not because it was just too faint?
Because I guess especially from GW 170814, it's relatively easy to predict if a source has a certain signal to noise and properties in the LIGO detectors, how bright it would be in the Virgo detector. And this source was extremely bright in both LIGO detectors, and I don't recall a number, but it should have been, according to the scaling, easily detectable in Virgo, but they didn't see anything. And the point is that this blind, well, actually, the Physical Review Letters paper states that they detected it at a signal to noise of 2. Fantastic. So you don't see anything at all in the image, and if you basically assume this is where it has to be and somehow, I don't know, put kind of a warped readout region on it compared to the background, you see that there's a tiny little blip summed over the whole thing. And but this blind spot region is relatively small in the sky, which managed to reduce the error banana of the two LIGO detectors by a lot. And in the end, I think the NGC galaxy was on the edge of the, or maybe a little bit beyond about the 90% error region. So it was on the edge, but it was still a good localization.
But just a thought. So you talked about the different strategies to try to find the kilonova, right? The tiling versus the targeted surveys. I mean, does it make sense? I can't remember the offset of the kilonova from the galaxy center. Do you remember that number?
10.2 Do you remember how that stacks up again?
Sort of the distribution of S GRBs.
It's actually a bit closer. to the core of the galaxy than most short
That's what I
GRBs.
thought as well.
In some cases, I can think of some papers by, say, for instance, Antonio Rowlinson, who showed very large offsets, and it was impossible to pin down which galaxy that came from. So I was just thinking, as you're giving the talk, if you're looking for something that might have a very large offset from its host galaxy, is the targeted approach actually the best way to do it? Because obviously that reduces the amount of time you spend looking, but maybe the DES approach actually was maybe the better one, in case this thing was offset and it had no apparent association.
For the tiling approach, there are two things you need. First of all, you need a huge detector, which somehow utilizes the telescope field of view as far as possible. And secondly, similar to PTF, you need a very large computing power to do the whole stacking, image subtraction, and search pipelines in almost real time to find these sources. So the point is that the DCAM survey did find the source independently of SWOPE and DLT40, and so even before Coulter et al. Announced it, they were just not fast enough in writing a GCN.
We're kind of lucky it occurred so close
to the host galaxy, because I don't think there are any emission lines or anything. I mean, if the thing, well, okay, I take that back. If it occurred far from a host galaxy, we'd have no way to pin down its distance, right? There'd be no spectroscopic redshift. So we got really lucky in this case in several ways.
Yeah. I seem to recall that in some spectra, maybe they see a very slight sodium absorption line from the host galaxy in the kilonova spectra, which is at the redshift of the host galaxy.
I mean, if this thing's offset, we wouldn't see anything like that.
Yeah.
As well.
Yeah.
So
we got very lucky with the fact it was so close to the host.
What you mentioned beforehand, there's this case of so-called hostless short GRBs, where you actually detect an optical afterglow. You have a sub-arcsecond position of the short gamma ray burst. You follow it up with big glass down to 27th magnitude or so, and there's absolutely nothing beneath it. And then you have like 4 galaxies, which are all moderately large at moderately high redshifts somehow around it, and you can't really decide which one is the actual host galaxy. And in such cases, then you just can't get a very good redshift, even though you had an optical afterglow.
Good talk, thank you.
Any other questions?
More questions?
It was a very nice talk. Thanks a lot. Very nice summary, and I have enjoyed it very much. Yes, I am very curious about the model that you said about. You mentioned about the radio mission, considering this cocoon, that you consider that this mission could come from this cocoon, and I have the curiosity to interpret that, considering that we have here a relativistic jet. Then I don't know how general can be this interpretation for other cases. It's something new, really, because you mentioned that today there was another paper in which they were interpreting that the radio emission was due to the scattering of the photons coming from the jet in this cocoon. Is that right?
Yes.
Yeah.
So first of all, I haven't really read all of this in detail. First of all, the cocoon itself was supposed to be the explanation for this relatively soft thermal bump that is seen in the gamma ray burst emission. And the question about the harder short spike is kind of still unsolved, because at least naively, I had mentioned beforehand that the jet opening angle only becomes wider once the jet has collided with interstellar matter and slows down. And according to the normal fireball model for gamma ray bursts, the actual gamma rays, this is also something that Zach mentioned briefly last week, the actual gamma ray burst itself is produced by so-called internal collisions within the shock of shells of slightly different Lorentz factor. And so you would expect that this occurs during the coasting phase of the jet before it has actually been braked down, and therefore at the highest Lorentz factors and the highest collimations. So you would expect of all emission associated with a gamma ray burst, the actual GRB itself would be the one that has the lowest chance of being detectable because it has the highest collimation. And so that might be an interesting point for the scattering model, is that what we were seeing as a hard spike was not really the prompt emission of the burst, but it was just like a shadow of, a light shadow of that was somehow processed by other matter and sent towards us. Maybe a bit similar to this detection of a reflection of the superflare of SGR 1806-20 on the surface of the moon by a satellite back in 2004, by a satellite which was on the other side of the Earth and did not have a direct line of sight to the flare itself. So it's perhaps very roughly something that is similar, but obviously this is something that is being studied. So I had mentioned that there are like 5 or 6 topics that are being worked on concerning this event, and each by anything between a few to a dozen groups. So there are a lot of papers on the off-axis modeling. So I was doing a bit of favoritism by showing our own model, but I think it's a pretty good one, and it delivers results which are in accordance to different other constraints on the opening angle and the off-axis angle. So this is in general still an unsolved problem that people will be working on.
This 2-second delay, this 1.7-second delay, I mean, and the fact that we don't know if it's a short or long GRB. I mean, if the initial spike is due to reflection or something else, then we can't really say much about the original burst of gamma rays, right? We don't know its original duration, do we? All we know is its reflective properties, if it comes from reflection of the cocoon.
Again, another paper a few days ago by Istvan Horvath and
colleagues
who claimed that this thing was a so-called intermediate GRB and not a short GRB, but I kind of have my doubts about the whole thing, because, I mean, again, Antonio in a paper showed that this so-called class of intermediate GRBs are basically just a subclass of long gamma ray bursts which are associated with typical type 1c broadline supernovae, and we are obviously not seeing a type 1c broadline supernova here. So the question is, I mean, the whole dichotomy of short versus long and the 2-second boundary is something which can lead to a lot of heated discussion. Greetings to Copenhagen. And so yes, it is of course possible that maybe the intrinsic burst was a few seconds longer, and we are just seeing the very hardest part of it as an initial spike or something like that. I mean, this is again similar to the detector probabilities, in the sense that like the first gamma ray bursts seen by the Vela satellites were all relatively short, because they always just saw the peak of the iceberg of the emission, and any fainter sub-emission we see today regularly with, say, Swift or Integrod was completely indetectable by those detectors. And this might, of course, be a similar case. But of course, what is definitely clear is that this source was a merger of 2 neutron stars and not the core collapse of a massive star.
Okay, thank you very much for this really very interesting talk, and to be so clear, even for the people that we don't work in gravitational wave or in GRB topics. So thank you. Let me thank